Hello everyone, welcome to our tutorial, Learning by Exploration. My name is Hongning Wang, an assistant professor from the University of Virginia. Today, it is my great pleasure to work with my students, Qingyun and Huazheng, to discuss with you about this exciting research direction. Although we have decided to pre-record this presentation, we do offer you live chat. So please feel free to type in your question or interact with us during the breaks. We'll be more than happy to share our experience and knowledge in this domain of research. We organized our tutorial in 6 parts. First of all, we would like to explain to you why we are so excited about this research direction, and in particular, why it is so challenging. Based on that, we will walk you through the classical solutions in this area of research, which will build up the solution framework we will present later in the tutorial for us to solve complicated learning problems in real world. For example, what if the environment is changing? And how do we handle the constraints in practical settings, like privacy, security, and safety constraints? And in the end, we would like to conclude our discussion and share our vision for the future research in this domain. Let's get started. Nowadays, thanks to the rapid development of artificial intelligence, our everyday life is surrounded by those intelligent systems. For example, if you just take a moment, look at things around you, I bet you can easily identify such systems, which provide us information and help us make more informed decisions. And due to the existence of such systems, they greatly improve the efficiency and productivity of our life and work. But as a practitioner of artificial intelligence, we have to keep asking ourselves, how far away is this intelligent systems to our human intelligence? And based on that, how can we further improve it? In order to answer those questions, we have to look behind the system, to think about the technologies that create those intelligence at the first place. And nowadays, the most popular used solution framework is a supervised machine learning, and it usually performed in the following way. First of all, we need to create a large training data set where we provide our annotations of our problem we're interested in. And then as a system developer, we have to manually craft the features, design the model, which usually can be formulated as an optimization problem. And then we try our best to solve this problem. Hopefully we can get a useful model. At the testing time, it gave us high performance, for example, high accuracy. And recently, thanks to the fast development of deep learning techniques, the barriers to build such systems get lower and lower, while the performance of such systems get higher and higher. In many applications, for example, in computer vision, the performance of such systems is getting so close to human or even beyond human performance. But we have to ask ourselves, are we satisfied? And clearly we know the drawback or limitation of the system is as obvious as the success of it. That is, the system only learns from what we provide. Or in other words, the learned system only knows what is already in the data. It still doesn't know what is not there. Let's take object recognition as an example. If you never provide any training data about cats, then we cannot expect this algorithm to automatically figure out this concept cat and then making predictions of cats. And under this paradigm, how do we solve this problem? I guess the only solution for now is then we provide such training data. But then, how about this second question? What additional training data should we provide to the system ahead of time? It seems the answer to this question is only clear when the system fails. But in practice, system failure often leads to catastrophic consequences, which we cannot afford. So when we think about this paradox, which are caused by the lack of knowledge about the problem space, we're actually not alone. because humans are always constrained by the knowledge they have about the world or the universe they live. But we never stop exploring the unknowns. We keep expanding the territory or the boundary of our knowledge, keep improving it. Let's take the example from the age of discovery. By then, our knowledge about the world was very, very limited because we even believed the world was flat. But the pioneers, they didn't believe so. They took sail to the unknowns, keep expanding it, improve our knowledge about the world. And then here, can we do the same to the machines? That is, let it explore the unknowns, expanding its knowledge so that they can help us make better and better decisions. And let us use recommender system as an example to illustrate this high-level concept we name as learning by exploration. In terms of recommendation, I bet most of you can name a dozen of algorithms or solutions to address this recommendation problem. For example, content-based collaborative filtering, matrix factorization, and even neural network-based methods. But all this sort of algorithms, what they are doing is trying to amplify the inductive bias in your training data. That is, if we found this group of users like horror movies, then recommend more horror movies to them. This group of users like romance movie, then just recommend more romance movie. But what happened to this kind of movies? The user didn't really rate or provide us feedback. They don't like it, so they don't provide feedback, or they didn't get a chance. Think about how the data was generated. The system takes the initiative to push the recommendation to them, and then they provide us the feedback. Is it just because the system actually didn't explore, didn't give the users the chance to tell us whether they like it or not? Unfortunately, this will make the systems victims of the Matthews effect. That is, the rich get richer, as the system simply amplifies the bias that already exists in the data, which can hardly optimize the utility of the users of such systems. How do we address it? How do we get a better understanding of the user's preferences so that we can maximize their satisfaction towards the recommendation? The answer here we provide is learning by exploration. We need to actively explore the unknowns. So hopefully we can better understand the distribution. So hopefully we can provide them better recommendation. But clearly, learning by exploration is not that easy. It's easier to say than to do it. First, the challenge is we are facing a huge search space. Again, let's take recommendation as an example. In movie recommendation, any working system will face a huge search space with tens of thousands of movies to choose from. We cannot imagine we ask a single user to rate or to watch every single movie and tell us which he or she likes. And oftentimes, its exploration is not free. Actually, it's quite costly, because just a couple of bad recommendations will keep your loyal customer to the competitor. So you don't want to do that, but you still need to or have to learn what you don't know. And because of this costly exploration, we often face this so-called bandit feedback. That is, we only got the answer to the questions we have asked. Well, for all the other things we didn't ask, we still don't know the user's preferences. Take movie recommendation as an example again. They say we only ask the user whether he or she likes the movie Titanic. If the answer, no matter the answer is positive or negative, we know little about the others. We have to keep asking the question to know the others. So as a result, efficiency of the exploration is very important. We have to be very careful to decide when and what to explore. Another important factor that makes exploration challenging is that observations we got might not be independent. So let's take movie recommendation as the example again. The movies themselves could be clustered, for example, by genre, by their directors or leading actors or actress. As a result, the user-provided feedback might not be independent or oftentimes highly correlated across those movies. And even the users themselves might not be independent as they are influencing each other on their choice of the movies. As a result, an efficient exploration strategy has to factor all this into consideration to explore the problem space so that to improve its efficiency. Another important fact about the learning environment is it could be non-stationary. In classical machine learning, we usually assume a stationary learning environment, that is, from which the data instances are IID sampled. However, in practice, in real world, the only thing constant is change. So everything is fast moving, fast changing. Then the system also needs to recognize the change of the environment, to recognize what has been out of date, and then to keep exploring these new things, to keep improving itself. But unfortunately, actually the system doesn't know when the change will happen, where the change will happen. Even for the parts we're quite confident of, by the past exploration, it might become out of date. That means we have to keep refreshing ourselves in order to handle the new challenges provided in the new environment. Last but not least, we have to handle or we have to respect all sorts of real-world constraints like safety, privacy, and ethical concerns. We cannot really arbitrarily explore the problem space, but instead, we have to fully respect the constraints and solve a constraint optimization to learn by exploration. So with that, we would like to move to the real technical discussion. How do we really handle the problem? How can we efficiently address exploration problems so that we can learn from the unknowns? To begin with, we'll walk you through a series of classical exploration strategies, which will become the foundation for us to build more complicated models to handle more real-world scenarios. So let's first formulate the problem. We will borrow the concept from multi-armed bandit to give you the first impression. What do we mean by learning by exploration? So imagine now we're building intelligent system like a robot here. The robot learns from the environment by taking actions. And here we will restrict ourselves to discrete choice of actions. So the agent take an action provided by the environment and then observe reward as feedback. And then the environment here we'll assume it's stochastic in nature. That means this reward is a sample from an underlying distribution. So by meaning learning this environment, we mean the agent need to figure out the reward distribution so that we can figure out what is the best action to take given this learning environment. And every time the agent gets exposed to a set of actions, and then by kind of a condition on the history, the agent need to figure out a policy to figure out at this moment what action to take is optimal at the best interest of this agent. And then the history includes all the actions the agent has taken and the corresponding reward. And the goal for the agent is basically to maximize accumulated reward over a finite time of interaction. And hopefully by the end, the agent will realize what is the best action to take. And then typically use the metric to evaluate the agent's policy is regret, or pseudo regret, which is defined as expected loss due to not playing the best round. As you can see, this is a cumulative metric, and the best we can do is to get a zero instantaneous regret. So reward is, the regret is always increasing over time. So the only way we could have is to increase slower. How slow will we desire? Sublinear regret. Why sublinear? Basically means if we consider this kind of average regret over time, a sublinear regret will give us a zero asymptotically regret over time. And can we really get to zero? Unfortunately, people have proved the lower regret bound is at least in the log t scale. So basically it means it's like the best case you can do is increase only in a log rate, and it's scaled by the difficulty of the problem. And the difficulty is very intuitive to understand. It's basically the gap between the optimal action and the second optimal. So the smaller this difference is, the more samples or iterations we have to take in order to really differentiate who is the best. And if you don't like this kind of problem-specific lower bounds analysis, we also offer you this kind of generic problem-independent lower bounds, which looks much worse. It's in the square root T order. That means you have to make at least this many mistakes in order to identify who is really the best action for this given environment. And of course, in this kind of problem-independent regret analysis, we have to assume finite variance. That means, okay, most of the time, what we got is really about the true reward distribution rather than noise. And as you might know, we also have a setting called adversarial bandit. That is, the reward is set by an adversary rather than some fixed stochastic distribution. But clearly, that's outside the scope of this tutorial, so we will now cover it. Interested audience can find related literature about it outside this tutorial. And in the multi-arm bandit setting, we basically assume this reward distribution is linked to individual or particular arms. Can we generalize it? We always prefer a prime model so we can easily go beyond what we have seen in the training data. And the answer is yes. We can also introduce features. Here we call it as context or context vectors to characterize options the agent has. And by assuming the reward distribution is governed by a function of this context vector and some sort of bandit parameters. As a result, we don't need to limit ourselves to fixed k-arm setting. And possibly we can extend it to infinite number of arms, where each arm will be characterized by a feature vector. So the agent will have an expanded history. For example, in the linear contextual bandit setting, we'll simply assume the expectation of the reward is determined by the inner product of the bandit parameter and the context vector. And then the history of this agent will be expanded by the arm, the feature vector, and then the corresponding reward in history that the agent has explored. And then accordingly, the agent needs to decide its policy based on the context vector in history and the reward in history. Will this make the problem easier? The answer is no. We're basically facing the same problem that the agent tried to maximize accumulated reward over T rounds, and then we still use the regret as a metric to evaluate its performance. And again, as we mentioned, lower bound analysis tells us this problem is not easy at all. It's still a square root T regret. And here, the scalar or the coefficient change from the number of arms K to the number of features D, which is expected because the more features we have, presumably we need more samples to estimate the corresponding parameter. And this might remind you, if we further abstract this problem setup, that is, the agent try to learn about this environment by taking actions. And then the environment will provide feedback in terms of reward based on the action being taken. If we just add one more thing into this kind of loop, we call it state. This might immediately map this problem formulation into the well-known problem setup, reinforcement learning. That is, if we assume some kind of state transition with some Markov decision process, then the agent don't need to carry the entire history. The agent only need to know what is the current state and take actions accordingly. And the reward not only decided by the action, but also the state. This gave us a complete Markov decision process. But clearly, this problem setup is broad, much broader than the bandit setup. So it's out of the scope of this tutorial. For interested audience toward this problem, there are tons of tutorials about this general problem setup, and we recommend you to refer to them for more information. In this tutorial, we will kind of constrain ourselves to this bandit setting. That is, the agent take actions with respect to the entire history, and the reward is provided by the given app, the given action. So we can consider this as reinforcement learning without state, or reinforcement learning with a fixed state. Then here, clearly, we have two important problems to think of. The first one is reward estimation, because it will give the agent some idea about the quality of the action. And in particular, in the multi-arm bandit setting, the convergence is most important. we need to figure out, just like as fast as possible, we need to figure out what is the best action. So we will just keep playing with this best action. And in multi-arm bandit setting, we can use mean estimation by assuming this kind of stochastic reward generation. And then for the contextual bandit setting, we usually solve a parameter estimation problem formulated as an optimization problem. We can specify problem-specific loss function and regularization. And then the convergence totally depends on the solver of this optimization problem. For example, in the linear contextual bandit setting, because of this kind of Gaussian noise assumption, we can use ridge regression, which gave us a nice closed form solution about the bandit parameter, which can lead to analytic regret analysis. Once we have the reward estimation, the next thing we should worry about is arm selection. What is the best arm to take for now, so we can better understand what is the optimal arm in this environment. So exploration matters, and this will be the focus of this whole tutorial. And then we have different perspectives to characterize the exploration. For example, it's adaptive or non-adaptive, with respect to the reward estimation. And it is kind of independent exploration or collaborative, so the agent can help each other to better explore its shared problem space. Or it is kind of unconstrained exploration versus constraint, like do we have the real world kind of ethical, privacy, and safety constraints. So we categorize those classical exploration strategies into 4 types. The first strategy is the most straightforward random exploration. Based on that, we kind of realize the limitation of them, and then we develop a second type, the most popularly used type of exploration, optimism in the face of uncertainty. And then we also have in parallel this kind of post-tail something-based solution, try to realize the uncertainty of parameter estimation from a Bayesian perspective. And then we also have this kind of a more active perturbation-based method, try to incorporate the uncertainty in arm selection. So let's get started with the first exploration method, that is random exploration. As the name indicates, basically we're exploring purely randomly. And the most famous random exploration strategy, as most of you might already heard, epsilon grading. So this algorithm is as straightforward as we'll illustrate here. At every iteration, when we need to take an arm, we just toss a coin. If we get a hat, for example, this kind of random variable takes the value 1, then we will use the current reward estimation to take the best action. That gives us the highest empirical reward. Otherwise, we'll just randomly choose an arm from the pool. Once we pick the arm, we'll observe the corresponding reward added into the history, and then update our reward estimation, and then repeat this. And by the way, because it's in the multi-arm bandit setting, the reward can be estimated by empirical mean of the history. And then we repeat ourselves. As you can see, the key in designing this epsilon gradient algorithm is this epsilon parameter. Clearly, if we just naively using a constant epsilon, it will lead to linear regret, because we will have a non-zero constant probability to take the second branch. That is, we randomly choose an arm. That means we randomly choose a suboptimal arm. So we don't want to do it. As we mentioned, we prefer some sublinear regret. How do we do that? So intuitively, we need to have a shrinking probability or shrinking epsilon. And technically, we can prove that if we set epsilon in this way, roughly speaking, in a rate of 1/t, we can guarantee a sublinear regret. And it's in the scale of its lower bound, still in the log t scale. So that's satisfactory. Just like at least theoretically, we prove this algorithm is not that bad. It's reasonable in terms of its distance to the lower bound. However, in practice, as we know, this algorithm is non-adaptive. So the exploration is independent of its current quality of reward estimation. So it often leads to suboptimal performance. So this is basically a starting point for us to do learning by exploration. We definitely need better solutions than that. A remedy for that is the so-called epoch grading. So instead of randomly exploring uniformly or at every iteration, epoch grading decide to only explore at the beginning of each epoch. And then after taking this random action, we will update the epoch-wise history and then compute the length of this epoch. Within this epoch, we will be greedy. We'll keep exploring the best arm so far until we run out of epoch. The most important thing here, within this epoch, we will not update our reward estimation. And then once we finish this epoch, we'll go back to the beginning of the epoch to do random exploration. So basically, we will do exploration for one step and then keep doing this exploitation for the entire epoch. So as you can imagine, then the key here is to design the epoch length so that we will have a reasonable balance of exploration and exploitation. So literature suggests if we design the length of epoch in this way, we will get a sublinear regret. And intuitively, the length of this epoch is related to the length or size of the hypothesis. That is, if we have only a few hypotheses, then we should fairly trust those kind of candidate hypotheses to exploit them more. So intuitively, just like as we have a shrinking size of hypothesis space, we should exploit it more often. This will give us a sublinear regret in the rates of t to the power of 2/3. As we know, okay, this seems like not optimal, as this kind of problem independent lower bound is t to the power of 1/2. That means there is still a gap for its kind of a performance. And then let's move on to the second family of the solutions, the so-called optimism in the face of uncertainty. Let's just briefly recap the nature of reward generation. It's stochastic. That means without enough observation, the reward estimation could be biased, could be incomplete. So we cannot simply trust it. Instead, we should consider the distribution of it, or confidence interval of it. That means within the confidence interval, or the true reward is very likely lying within it. And to prove the concept, basically we can use the Hongning bound. So with finite number of the observations, the average of the reward is getting close to the true reward with this gap. So that means the true reward is within our confidence interval, or everything within the confidence interval could be our true reward. So instead of just trusting the mean, can we be more aggressive? Let's trust the upper confidence bound. Trust the highest reward that is possible within the same confidence interval. So we could encourage the currently underestimated arms. And then this gave us this famous upper confidence bound based exploration. So intuitively, there are two parts in this exploration strategy: the mean reward estimate so far and the confidence interval, or the so-called confidence bound. If the mean reward is low, but the confidence bound is large, that means, okay, this could be an underestimate arm, so we should give it some hope, give it some chance, see whether it will turn out to be a better arm. And this algorithm turned out to be very effective. In terms of its upper regret bound, it basically matched the lower regret bound. For example, in this kind of problem-specific lower bound analysis, so we have the matching term of log p regrets. And for this problem-independent upper bounds, we see we have an actual log t term. That means, okay, there is indeed a gap between the lower bound and upper bound, but this gap increases slower. So to understand this, let's use epoch greedy as an example. So in epoch greedy, its problem-independent upper regret bound is in the order of t to the power of 2/3, compared to the lower bound, t to the power of 1/2. The difference here is t to the power of 1/6. Clearly, it's much larger than the log p factor here. And then in this kind of UCB1 algorithm, it's for multi-unbounded. Do we have a corresponding version for contextual bandit? The answer is yes. We need to have the contextual version of reward estimation and the confidence interval estimation. So let's use the linear bandit as an example. Here is our reward generation assumption. It's kind of expect reward is computed by the inner product of the context vector and the bandit feature vector. And the reward is somehow contaminated by a Gaussian white noise. As we mentioned before, we have closed form solution, basically the ridge regression. Then we can estimate the bandit parameter, and use it, we can get the mean reward estimation. Because of this closed form estimation, we also have analytic convergence analysis, so we can quantitatively evaluate the confidence interval. And the expression for the confidence bound is like this, where we have an important parameter called confidence ellipse. And here we see this kind of confidence interval increase slow in time. It's only a log-t order. And because of this fast convergence of parameter estimation, we could have a sublinear regress. And if we compare with the lower bound of a linear contextual bandit, we see the match only with a log-t term. That means, okay, the upper bound is kind of above the lower bound, but only with a slowing increase in term. So that's satisfactory for practice. And if you don't like linear rewards, just like why everything has to be Gaussian, then we do have an option for you to go to the generalized linear model. That is, for example, in the problem, if we have discrete reward, like a binary, click or not click, like a dislike, and then we can introduce a link function using this generalized linear model. For example, for discrete reward, we can use logistic link function to map it. And as we all know, for generalized linear model, we might not have, oftentimes we don't have a closed form solution. But for most of this link function, especially for exponential family link functions, we do have next property of them. For example, for logistic, we know it's log concave. So gradient descent will give us a global optimal, and we know the convergence rate. So we can plug in this gradient descent back into our reward estimation and confidence interval estimation. And for the reward estimation, it's straightforward, just replace it with the link function. While for the confidence interval, we have a similar concept of this confidence ellipse, especially for logistic link function. And correspondingly, we have a very similar upper regress bound. The only thing is it looks slightly worse because it's scaled by this log-d factor. Based on this kind of a discussion of a UCB type algorithm, hopefully you got this kind of concept. We need to consider not only the mean estimation, but also the variance, so we can somehow construct the confidence interval. Then you might naturally ask, can we directly compute the confidence interval? Or can we directly compute upper confidence bound? And the answer is yes. So under this notion of KL divergence, we can explicitly compute the upper confidence bound. And then with this computed upper confidence bound, we can directly take the actions explicitly. And here, we just need some kind of a specific assumption about the reward distribution. For example, it has to be bounded in a range. And then we don't have enough time to really walk you through the details of how to directly derive this upper confidence bound. But here we'd like to offer you some intuition. For this kind of mean reward estimation, the KL divergence can be upper bounded using this log ratio terms. While using this Pinsker inequality, we can upper bound the square difference of the two distribution by KL. So if we put these two inequality together, you will see actually we have a very similar form, just like in UCB1. That is this kind of difference of the reward estimation square difference is upper bounded by this log term. And if we take the square root and move the empirical estimation to the right-hand side, that's basically our UCB1 formula for upper confidence bound. So instead of just like directly computing the upper confidence bound, a nice property of this exploration strategy is proved upper regress bound. We can prove it's asymptotically optimal. Let me show you the lower regress bound of an MAB problem. They basically have the exact same form. So basically means asymptotically, this algorithm achieves the best performance this type of algorithm can achieve. And then based on this concept, we got the idea we cannot simply trust the mean estimation. We have to consider the variance. We have to consider the uncertainty. And then the source of uncertainty, of course, comes from the stochastic nature of reward estimation, but it's reflected in the uncertainty of bandit parameter estimation. So can we directly model this uncertainty in the parameter estimation? That is, can we assume this parameter is no longer a single point, but actually a distribution? By imposing the prior distribution, so we can estimate the posterior of this parameter so that we can directly estimate or calculate the reward distribution. And to give you some kind of concrete example, let's use linear bandit as an example. So we assume the reward is generated by some Gaussian noise on top of inner product of the bandit parameter and the context vector. And then by assuming the prior of this bandit parameter follow Gaussian or zero mean Gaussian, we have analytic posterior. And this analytic posterior might remind you something, because the mean of this posterior is exactly the ridge regression estimate or our NLE estimate of this parameter. And a step further, the induced predicted distribution of the reward has this nice form, which is exactly what we have in linear CB. It has two parts. The mean is basically the mean estimation of the reward. And then the variance part is basically our CB. So as you can expect, the performance of Thompson sampling-based method should be very close to linear CB. And as we can prove, it is indeed very close. And if we take a close look at this upper bound, we see it just like differ a little bit. It's slightly worse theoretically than linear CB. But in practice, because the exploration in Thompson sampling is more aggressive than linear CB, empirically, oftentimes outperform linear CB. And you might ask, okay, in linear CB, we can expand it beyond the linear reward assumption to generalize the linear model. Can we do it the same here in Thompson sampling? And then the immediate kind of bottleneck is, how about the posterior? If we have conjugated prior just in Gaussian, and then we can easily do posterior sampling for Thompson sampling. But what if we don't? Can we still do bandit learning? The answer is yes. We'll do the same as we did before in the classical surprise setting. We approximate the posterior. We can use your favorite approximation method like Gibbs sampling, particle sampling. And then once we approximate the posterior, we sample from it and then compute the reward, take the action that has the highest reward. Empirically, it works well, but the problem is we don't know how to prove. Basically, we have very limited study in this area, how to prove the upper regret bound for the approximate inference in Thompson sampling. We do have some analysis from the perspective of Bayesian regrets, but this is outside the scope of this tutorial, so we will leave it for the interested audience to explore on their own. The last family of solution we would like to cover in this tutorial is this so-called perturbation-based. Again, let's come back to the principle of optimism in the face of uncertainty. We know the mean reward estimation cannot be trusted because we might not have enough observation. We have to expand it by the confidence interval so we can cover as much as possible. And then can we kind of directly introduce the variance or introduce control the variance? So some quantity we estimate naturally takes care of exploration and exploitation. And the answer is yes, by introducing pseudo reward. The way we do this kind of perturbation is every time when we take an action, not only we use observed reward to update the model, but also introduce some kind of high variance observations, so that we can prove this kind of a perturbation encourage underestimate arms, and it will not affect the concentration of reward estimation. For example, if we do this type of perturbation, we can easily prove a concentrate as a scale and a shifted version of the mean estimation. And also it's overestimation with a high probability. That means we encourage those underestimated arms to be chosen. And nice property of this type of solution is then we don't need to explicitly compute the so-called confidence interval. We can still use this kind of perturb. We can directly use this perturbed mean estimation for the reward. And surprisingly, people prove this type of perturbation gave us exactly the same upper regret just as UCB1, where we explicitly compute the confidence interval. And then you might ask, then this sounds great, but this is for MAB. Can I do the same thing for linear contextual bandit? And the answer is affirmative. Yes, we can. So basically, we will do the same thing to introduce pseudo reward into the history of parameter estimation. And for example, for the linear contextual bandits, we're doing rate regression. So while we are performing rate regression, we directly introduce the pseudo reward to history. So we'll have this perturbed version of the parameter estimation. We use it to directly estimate the reward and take action that has the highest reward computed in this way. And again, we can prove this is still encourage the model to give overestimation for the arms with high probability, and this will not affect the concentration because it will still concentrate at the scale and the shifted version of the true reward distribution. And again, the regret is the same regret as linear CB, that computation-wise, we only need to do reward estimation rather than the confidence bound estimation. The last piece of research that we would like to discuss in this section is the so-called perturbed adversary. Actually, the original motivation of this research is not to develop yet another exploration strategy, but to answer an interesting empirical finding. So let's start from the question you might already have in your mind while we're discussing the so-called exploration. That is, what if I just use a greedy solution? I trust my ridge regression. I trust everything I have done so far in history, and then just take the action accordingly. What will happen? A standard answer in textbook is please don't do that. Otherwise, you will encounter linear regret. But people found that in practice, this greedy solution oftentimes lead to reasonable performance, even quite comparable to all those exploration strategies. So what happened here? Were we just lucky? And then this group of researchers, they try to answer, yes, we are indeed lucky. This started from the perspective of generation of context vector. So you assume the context vector generated by some adversary, they could be adaptive. But before presented to the learner, these context vectors are perturbed by a finite variance distribution. For example, here, we assume it's a zero mean Gaussian. And in addition, this context vector has to satisfy two important conditions. First is after this perturbation, we got enough information on every direction of the problem space. So intuitively speaking, the minimum eigenvalue of the covariance matrix is lower bounded by some value. That means we are not short-sighted to any of those directions. Another important condition to satisfy is the so-called conditional margin. That is, at the time where we choose the best arm based on its expected reward, its gap is indeed the largest. That means the reason we choose this arm is not because of the noise introduced by perturbation, but by its true expected reward gap. If those conditions could be satisfied, they prove actually a greedy algorithm's regret is in the same order of a contextual bandit, a linear contextual bandit in this case, with more linear CB. It's only scaled by the variance of the perturbation. So that's a quite surprising, amazing result that indicates that is in such a benign environment, even a greedy algorithm could be a very good solution for learning by exploration. It also shed light on the possibilities for us to actively introduce perturbation to the context vector, just like what we did in perturbed history exploration, where we introduced the perturbation to the reward history. So this might allow us or enable us to do exploration with some complicated model, like deep neural networks. Okay, here are the kind of all the important techniques we would like to cover, which will build a foundation for the later part of the tutorial about how to handle more complicated real-world problems. Here are the references of this part of the talk, and we will take a short break for you to ask us questions if you have any. Thank you.